Hello everyone. So let's talk about greedy scheduling. This will be our first greedy algorithm. So this set of slides is an introduction to greedy algorithms. We'll focus on greedy scheduling, and we'll look at a way to prove greedy kind of algorithms using an exchange argument. And there is an activity or exercise associated with this set of slides. Okay, so what is a greedy algorithm? It's any algorithm that's making a myopic decision and just sort of hoping that it works, or we can prove that it works, but that's kind of the idea behind it. You make a short-sighted decision, and you never go back to sort of double check or check alternatives. So we can contrast this with divide and conquer. So it's typically easier to create greedy algorithms because you just come up with like a simple criteria that measures or predicts each of the different possible outcomes, and then just pick the best of all possible outcomes. And it's typically easier to analyze greedy algorithms. The code is typically simpler as well. But unfortunately, it's often harder to prove the correctness of greedy algorithms because you've got to find some way to say that out of all possible alternatives, we definitely chose the correct one. It's also possible for greedy algorithms to be incorrect, and sometimes that's okay. So later in the semester, we'll talk about approximation algorithms. And a common way to create an approximation algorithm is to have it be greedy-based, just because it's such a simple paradigm for creating an algorithm. Okay, so proofs of correctness, sometimes it can feel more like an art than a science. Compare what we're doing in this set of slides to what we did for divide and conquer. So for example, quicksort, we looked at sort of counting the number of comparisons. In merge sort, we looked at the recursion tree. Compare that to what we do here. What we normally will do for a greedy algorithm is do a proof by induction on the greedy decision, or a proof by induction on an exchange argument, which is something we haven't looked at, either by contradiction or by exchanging with some sort of optimal solution. Basically, we just want to do whatever works. And this will make a lot more sense with examples. So let's talk about 3 or 4 greedy algorithms. The first being, well, actually, before we get into the next slide, which tells us our new algorithm that we're going to discuss, we actually know one greedy algorithm. So we've seen one before in this class. Let's see, I'll put a pause here in the video so you can think about it and see if you remember which algorithm we've discussed already is a greedy algorithm. Well, your hint here is that it was a graph-based algorithm, and your second hint was we actually had greedy in the name of the algorithm. So we have Dijkstra's algorithm, and within that we had Dijkstra's greedy criterion. So for example, finding the optimal length from the start vertex to W, Dijkstra's would tell us to go this way, and the reason it would tell us to go that incorrect way is because it's a greedy algorithm. It doesn't find this other path. At the very beginning, it chose this edge at the bottom, and it never went back to reevaluate whether that was the correct edge. So the path length using Dijkstra's, it would have given us a path length of 2, whereas the correct shortest path for this set of vertices would be just 1. Okay, so let's talk about another sort of application of a greedy algorithm. So we'll start by talking about scheduling. And this is going to be a very simplified view of scheduling. We're going to ignore things like concurrency, where you can have one process running for a certain amount of time and then preempt it and put another process in its place and run on the same hardware. But we're going to use that as an example because I think it sort of makes it more easy and tangible. So let's say that the shared resource we have is a processor, and we have a list of jobs that need to use the processor. So we want to execute some programs. And each job is going to have a priority, so that's how important the job is. So maybe it's more important to interact with the user or react to the mouse clicks than it is to run something like an audio clip. I don't know. Each job is going to have its own importance, and it's also going to have a duration. So we're going to know how long a job takes to run. So in what sequence should we complete the jobs? So the assumption here is that we have, I don't know, 10 jobs, let's say, and we know the priority and duration of each of them. How do we schedule them? How do we put them in order? Well, to understand this a little bit better, let me give you a few more things to think about. So again, that's our question. In what sequence should we complete the jobs? What is our criteria, though? What are we trying to optimize? Are we trying to say all higher priority jobs are scheduled first? Or are we trying to say, well, let's get the short jobs done with, so let's schedule them first? Should we do the long jobs first? We have to figure out what we're trying to optimize. So for this, I'm going to say we're going to optimize the completion time. And that's not something I mentioned on the previous slide. So each job is going to have a priority, a duration, and now it's also going to have a completion time. And the reason that we can't say that the completion time is a property of a job is because it's going to depend on the other jobs as well and the order in which they're scheduled. So let's say we have 3 jobs and their durations are 1, 2, and 3. We can ignore their priorities just for a moment, because all I want to talk about is how do we come up with this completion time property. Well, let's say that we schedule them in order. Well, if we schedule job 1, which has a duration of 1, that means its completion time is also 1. But job 2, if it's scheduled next, it happened after job 1, so we have to take the total duration of job 1 plus the total duration of job 2 to get a completion time for that one of 3. And then likewise for job 3, it takes the 1 unit of completion time from job 1, the 2 from here, and the 3 from here to give us a total completion time of 6 for job 3. So if I rearrange these, each of these jobs would maintain their same priority and duration, but they could have different completion times. So let's focus in on one particular job here. What is the completion time of job 5? So what I'm trying to get you to think about with this slide is on what does it depend? So maybe that's a good place to start. Well, hopefully as I'm writing that out, you started to think about it. If not, feel free to pause it here. But you should notice that it doesn't depend on this at all. So it just doesn't matter for the jobs that come after it. The completion time of job 5 is just equal to the duration of job 5 plus the sum of durations of all the jobs that were scheduled before it. And I'm not going to say if that's equal to 1 up to 4 because there's no reason that we have to execute jobs in order. So we'll just say the sum of all the completion times of jobs that came before it. Okay, so we know what each job's completion time depends on. Actually, I think I'll break this video here.